So welcome students to part 3, and in this part we are going to be talking a little bit about the muscular response. So in order to record a muscle contraction, patients could be hooked up to an electromyogram or an EMG device where they would be stimulated through the skin. They would get this very minimal electrical stimulation. It does not hurt at all, and that would lead to a muscle contraction. And we could record the electrical changes and the contractions that happen, and we could see it on a device. It's kind of like the EKG where we record the electrical changes of the heart. In this case, we are recording the electrical and the mechanical changes that are happening in the muscle. But in order for that to happen, the muscle has to reach what is known as a threshold stimulus. So when we stimulate the muscle, if that stimulus was below that threshold level, no contraction will occur. But if the stimulus was at or above that threshold stimulus, that's when the muscle contracts. And remember that the contraction of the skeletal muscle really is mediated by the release of calcium from the sarcoplasmic reticulum, and that again would activate your cross bridges. Once that the motor neuron will release the acetylcholine, and if enough acetylcholine attaches to enough of those cholinergic receptors, where we reached the stimulus, that's when a muscle will respond, and we will see that response in the form of a contraction. So this is what a muscle twitch would look like. So if we isolated one muscle fiber, stimulated, so, gave it a little bit of electricity, and recorded what is going on in that muscle fiber, we get what is known as a muscle twitch. So the twitch is basically the contraction of one single muscle fiber. And so let's take a look at what we're looking at. We are plotting time against the force of contraction. So this is when the stimulus was applied. It takes a little bit of time before the muscle actually responds to the contraction or responds to the stimulus. And that a period of time where nothing is happening is known as the latent period. So we see it on the graph as nothing happening, but what is really happening is that the acetylcholine is being released. It is swimming across the synaptic cleft. It is activating the acetylcholine receptors. Calcium is being released, and that whole story that we talked about in part 2, all of that is happening during the latent period. And followed by a period of contraction where we have the sliding filaments of the actin on myosin, and then followed, last but not least, by a period of relaxation where the calcium again is being removed and the myosin heads release and let go of the actin fibers. You can see here that the period of relaxation takes a longer time than contraction to happen. So contraction is much faster than relaxation. Now, what is the length-tension relationship? That is the relationship between the length of the muscle before it contracts and the strength of the contraction, or the amount of tension that muscle can produce. So, in order for a muscle to contract, you want the muscle to be at what is known as the optimal length, where there is space for sliding, and the myosin heads are able to attach to the actin fibers and lead to the shortening of the sarcomere. Okay, so this is your optimal length at rest. But if your muscles are overstretched, so think of trying to reach something that is really high and you're overstretching your arms to reach it. At this point, you are really pulling these fibers away from each other. Okay, so these myosin heads will try to bind to the actin, but they're pulled away, they're pulled too far away from each other. So that would, as you can see here, will give you a lower strength of contraction or lower tension of the muscle. While on the other hand, if you overly shorten the muscle, you see here that there's really nothing left here to shorten. The muscle is already shortened enough where there's no more space to further shorten or to further contract. Okay, so again, you want the muscle, before contracting it, you want it to be at this optimal length. So think of the weightlifter. So if you've ever watched or if you've ever personally done weightlifting, you will be trained on how to position your muscles to get the most out of your muscles. And that again is your optimal position to put these muscles at the optimal length at rest, so before contraction, in order to produce the greatest force upon contraction. So again, this is your length-tension relationship. So the relationship between the length of the muscle before contraction to the amount of tension or pressure produced upon contraction. Now, what is summation? So when we contract, we don't really contract individual muscle fibers, okay? We don't do these individual twitches. Lots of muscle fibers contract together, and those are all summed up together in order to give us a movement, and that is known as summation. So summation is where we are producing the force by adding up all of those individual muscle twitches together, combining them together to give you a muscle movement. So here is what individual twitches would look like. When we contract your muscle again, you do not contract and then relax, and then contract and then relax, and so on. You have this very smooth kind of contraction. And that is, again, is because you're summing up twitches, individual twitches together to produce a smooth contraction, followed by obviously going back to normal, which is relaxation. Okay, so this is known as a partial summation or partial tetanic contraction, where you do sum up twitches, but then you go back to relaxation. On the other hand, you've got complete tetanic contractions, where you're summing up a whole bunch of muscle twitches, but there is no relaxation, and that is what occurs during tetany. So the tetanus toxoid, the tetanus microbe or the pathogen, leads to the summation of the individual twitches. So you do have lots of contraction, but no relaxation. Okay, and that again is known as your complete tetanic contraction. That could be lethal due to the tetanic contractions of the respiratory muscles, and that could lead to respiratory failure. Now for recruitment of motor units. So what is a motor unit? We talked about a motor nerve, we talked about muscles, muscle fibers, but we never mentioned a motor unit. So the motor unit is the motor nerve plus the muscle fibers that it innervates. So if we take a look at this motor unit number 1, it's made out of that motor neuron and these purple fibers. Okay, so this motor neuron innervates all of these purple fibers. The second one, motor unit 2, you have this one motor neuron that innervates all of the red ones. Okay, so each motor nerve has the ability to innervate more than one muscle fiber. When you add up the motor nerve plus the muscle fibers that are innervated by that nerve, that is what we call a motor unit. Now, motor units are different from one muscle to another. So, for example, if you need these very coarse kind of movements, so think about your back muscles. Back muscles are pretty much, you don't need like these fine movements of the back. Usually we are either standing or sitting, and the back muscles are give us more of this coarse movement. So we would have bigger motor units where each motor neuron would innervate a bigger number of muscle fibers. When you compare that to, say, the fine muscles of the hand, where you really need those fine motor skills in order to write or type or so on. So when you have these very precise movements, you have smaller motor units. So this one motor neuron would maybe innervate 2 to 3 muscle fibers, compared to the back, where one motor neuron would maybe innervate 100 or 200 muscle fibers. Because again, the more precise of a movement you need, you would want these smaller motor units in order to give you that control and preciseness that you can get. Now, how do we recruit these motor units? Know that the body is a very conservative thing. It's a very conservative being. It wants to conserve its energy. So what it does, let us say that I'm going to try to carry, let's say 50 pounds, okay? My motor nerves or my body will try to recruit the smaller units first. Obviously, that won't be enough for me to carry the 50 pounds. The next step would be to activate and recruit more motor units. Okay, if I can't still do it at that point, it will keep on recruiting motor units, one at a time until I reach a point where I've either recruited all of them and I still cannot carry it, or I reach a point where I am able to carry it and no more recruiting is going to happen. So again, because the body is so conservative, it wants to do the job with the least amount of energy and the least number of motor units. Okay, so recruitment again is the increase in the number of motor units activated to produce more force. Certain motor units, the smaller ones, are activated first. Okay, and if that fails, we can start activating the others so that we are increasing the force of contraction gradually. As the intensity increases, the recruitment keeps on going until all of the motor units are activated. So at that point, again, either I was able to carry the 50 pounds or not. In sustained contractions, so as we said, we recruit the first motor neurons to be recruited are your smaller ones, followed by the larger motor units. We are going to recruit and sum up all of those contractions together in the process that we called summation in order to produce a sustained contraction. So when I'm trying to, again, carry that 50 pounds, I try and then I fail, and then I recruit more fibers, sum that up, and try again. I do not relax the muscle and start from scratch. Okay, so it is kind of like going on that step one at a time without going backwards. And that's what it means when we say summation and recruitment can produce a sustained contraction of increasing strength. So sustained contraction means that you are not really relaxing the muscle in between. And the whole muscle contractions are smooth movements. So we do not get these contraction, relax, contract, relax. It is more of a very gradual recruitment of the muscle fibers. And these are things that kind of happen on a subconscious level. We don't really feel the muscle recruitment. Muscle tone, on the other hand, or tonus, is a state of partial contraction. So we are really lying when we say that the muscles contract and then relax. Our muscles never relax. They are always in a state of partial contraction, and that is what tone is. Our muscles fully relax when we are in certain stages of sleep, okay, or loss of consciousness. But while we are awake, and even during certain parts of even sleep, our muscles are in a state of partial contraction, and that again is referred to as muscle tone. And you could see identify muscle tone by, let us say, if you've ever tried to carry, say, a baby or a child. Let's stick to the child, okay? So if you ever try to carry a child when they're awake versus when they're asleep, Okay, when they're awake, they do have muscle tone and they are lighter, but when you try to carry them when they're asleep, especially if they're very deeply asleep, they have lost their muscle tone at that point and they are much heavier and it's harder to carry them. So what happens when we contract a muscle? Well, usually we are going to move a joint, okay? And it depending on what kind of joint it is, that would lead to different kinds of movements. And we already discussed that when we talked about joints in chapter 8. And it also depends on the way the muscle is attached. So we'll talk about that in the next slide. So each muscle has two attachments, or at least two. There's an origin, and that is your beginning. And then there's an insertion, and that's the end of the muscle. So the origin, again, is where the muscle starts. Okay, it is the less movable of them. It's the more stable or fixed part of the muscle. And then you have an insertion, and the insertion is the movable side of the muscle. When you contract, and you can see this is your biceps muscle, and it crosses over the shoulder and the elbow. Okay, so when you contract the biceps, the biceps muscle has the ability to move the shoulder and move the elbow. So in order for a muscle to cause a movement in a joint, it has to cross over that joint. When you contract a muscle, you bring the insertion closer to the origin. So the origin, again, is the fixed end, while the insertion is the movable or the mobile end. Now, the interaction of skeletal muscles. So we have a whole bunch of muscles, and a lot of them overlap in what kind of actions they can produce. So for example, and I'm going to go to that example of the biceps muscle and elbow flexion. So the main elbow flexor is biceps, but we have other muscles that can produce elbow flexion. For example, brachioradialis, for instance. So both of them can do the same function, and that is why for each movement there is a prime mover. The prime mover would be the main performer, which in the case of elbow flexion would be the biceps. Okay, so the prime mover, again, is the main muscle that would perform the movement, while the agonist would be a muscle that would help the prime mover. Okay, sometimes we use them interchangeably. We even sometimes use it like as a synergist muscle. So your prime mover, again, was the one that performs the main mover. Okay, your agonist is a muscle that can also perform that action. Synergist is a muscle that assists the prime mover. So in the case of elbow flexion, we have biceps is your prime mover. Brachioradialis would be a synergist. We can also call the biceps an agonist because it causes that elbow flexion. An antagonist movement would be a muscle that produces the opposite of the prime mover. So using that same example of elbow flexion, the antagonist would be triceps because it extends the elbow. And you can use this, these terms for any different for other movements. So if you flip the movement, if we're talking about elbow extension, for example, your prime mover would be triceps, while your antagonist would be biceps. So it all depends on what kind of movement you're talking about. Now, different kinds of contractions that we have, before we go over them, you need to know that when you contract a muscle, you are going to change one out of two things. Either the tone of the muscle or the length of the muscle. Not both. So either changing the tone or changing the length of the muscle. Usually contractions lead to change of the length of the muscle, and that's why we're moving. That kind of contraction is known as an isotonic contraction. Iso means the same. So in an isotonic contraction, the tone is not changed. The tone remains the same, but we are changing the length of that muscle fiber. When we change the length, we are moving a joint. Okay, and that could lead either to concentric or eccentric contractions. A concentric contraction would be like this one right here, where we are flexing the elbow and that movement is going upwards in the direction of elbow flexion, where we are bringing the movement towards the body. An eccentric contraction, like in this image right here, the movement is downward, so we are extending the elbow. That is known as eccentric contraction or lengthening contraction. So although the biceps muscle is increasing in length, but it is a calculated increase in the length of the biceps, so that we are not just unfolding or extending the elbow where we're pretty much just letting this fall to the ground all of a sudden, but it is a very gradually calculated kind of extension. So in that kind of extension, you are definitely using the triceps to extend the elbow and the biceps to make sure that it is a gradual, smooth elbow extension. So in an eccentric contraction, you are going further away from the body. Now this one is your isometric contraction. So iso again means the same, metric means the length. So you are not changing the length of the muscle, but you are changing the tone of the muscle. So for example, if you are trying to contract the muscle while holding on to this bar, that would lead to no movement, but the tone in the muscle will increase. Or think of arm wrestling, okay, where the hands are locked and there is no movement, but there is definitely increase in the tone of the muscle. Now, different kinds of skeletal muscle fibers. Remember, all of what we've been talking about throughout the chapter so far are skeletal muscles. So we have 3 different kinds of skeletal muscle fibers. There are slow twitch fibers, and those are known as type 1. We have fast twitch fatigue resistant fibers, and those are type 2A. And fast twitch glycolytic fibers, and those are type 2B. So let's talk about type 1 or slow twitch fibers. Again, think of your back muscles when you think of these fibers. So slow twitch fibers are the fibers that contract for the majority of the day, which means they are resistant to fatigue. Okay, they are always oxidative, meaning that it needs oxygen in order to go through cellular respiration. They've got a very good blood supply, lots of mitochondria, lots of myoglobin, and myoglobin is dark in color, so it'll give these fibers that redness in color. And it has a very slow ATPase activity. So although it does have the ability to contract throughout the day, the ATPase enzyme goes at a very slower rate, and that's why these muscles are slower to contract. Okay, again, think of your back muscles, fatigue resistant. You're contracting your back muscle throughout the day, whether you're sitting, standing, or so on. Very good blood supply, red in color. Compare that to these fast twitch ones, and I'm actually going to talk about the fast twitch glycolytic fibers type 2B first. These are anaerobic fibers. Okay, so they will go through glycolysis, and from their name, that's where the name glycolytic comes from. These are going to do a very fast twitch of a contraction. They have a very poor blood supply. They have very few mitochondria. They are very susceptible to fatigue. And because they have that fast twitch contraction, they have a very fast ATPase activity. Now, these are the fibers that you want to think of when you watch or when you sprint, okay? So when you're sprinting, those very first fibers that get you started, those are the fast twitch glycolytic fibers type 2B. So again, they are able to contract very fast, giving you that, sprint that you see at the very beginning or that you perform at the beginning. They are susceptible to fatigue. So a lot of the times when you watch a race or when you're racing, you start that sprint and then you get a cramp. Okay, that's because of the poor blood supply and the fewer mitochondria that are found in these fibers. These fibers are supposed to get you sprinting, and these will make you finish up the race. Okay, these fast twitch fatigue resistant fibers, or type 2A. These are pretty much in the middle. So their blood supply is intermediate. They are, kind of intermediately when it comes to how fatigue resistant they are. The activity of ATPase, though, is a little bit on the faster side. Their ability to break down glucose is intermediate, so somewhere in between the other two kinds. And the speed of contraction, again, of these fibers is intermediate between these two. Okay, so again, sprint running, the type 2B fibers will start you off, and the type 2A fibers will get you through the rest of the race. So little clinical application, the use and the disuse of skeletal muscles. So when you're bodybuilding and you are contracting the muscles, with either lifts and so on, that leads to the enlargement of the skeletal muscles, and that is known as hypertrophy. So hyper is bigger. Trophy means the size. So the hypertrophy is the enlargement of skeletal muscles due to the exercising. Atrophy, on the other hand, is the decrease in size, and that usually happens due to the disuse of skeletal muscles. And muscle atrophy can even happen during, if somebody is in a cast for too long. Okay, so when they remove the cast, they can find like a difference between the muscles on the other side, okay, compared to the muscles on the other side. That again, so just not using muscles for even a couple of weeks can lead to muscle atrophy. And that is why one of the main things that you want to tell your patients would be to make sure that they are always doing these aerobic exercises to keep their muscles healthy, to keep the blood flowing, and so on. The aerobic exercises are going to increase the capillaries, which increases the blood flow, and increase the mitochondria. Forceful exercise, so using weights and such, that can also produce new actin and myosin filaments, and that increases the ability to carry bigger weights, as time goes by. So at this point, I'm going to stop, and then we will go over the fourth and last portion of the chapter.